In this video, we present the design of synchronous binary counters. A synchronous counter, usually it has common clock that is applied to all flip-flops, and that's where the word synchronous came from, because the flip-flops are synchronized through the clock. And this is different from the ripple counter because the clock skew does not add up. In other words, all flip-flops get changed at the same time, exactly at the edge of the clock, whether it's falling edge or rising edge. And this type of counter is faster than ripple counters, also due to this reason that all flip-flops are changed at the same time, different from the ripple where each flip-flop will make the next one change. The design of synchronous binary counters is so simple that we don't need to go through through the sequential logic design process which we described earlier. However, we can use the same process if we want also. The feature of the counters usually is as follows. The flip-flop in the least significant position is complemented with every pulse. Let us look at the count sequence here. The first bit is first 0, then 1, then 0, then 1, 0, 1, and so forth. So that's what we mean. The flip-flop in the least significant position will be complemented with every clock pulse. However, a flip-flop in any other position is complemented when all the bits in the lower significant positions is equal to 1. Again, let us look at the count sequence. When this bit is 1 here, the second bit is complemented, so it goes from 0 to 1. Same thing here. When this bit is 1, this bit is complemented, which means it goes from 1 to 0. Again, when this bit is 1, this is complemented, goes 0 to 1, and with this 1, this complemented, and so on. So that's for the second bit. How about the third bit? The rule is as follows. When these two bits are ones together, this will go from 0 to 1. So we count from 3 to 4. Same thing exactly here. When these two bits are 1, this bit is complemented, so we go from 7 to 8, and so forth. Same rule we can continue, which means whenever these 3 bits are 1s, we will complement this bit, so we go from 7 to 8. Same thing when these bits are also 1s, this bit will be complemented, so we go from this to 0, 0, 0, 0 as an example, so we complement this bit. So this rule is very important to understand in order to be able to design. The counter can simply be designed as we see in this logic diagram, which comes exactly by following the previous rules that we have just described. In this diagram, we use JK flip-flops, and we call the flip-flops A0, A1, A2, and A3. So the counter will be A0, A1, A2, and A3. A0 is the least significant bit, and A3 is the most significant bit. And we have one common clock that is connected to all the clock inputs of the flip-flops, as we can see here. Now, the design, as we mentioned, the first flip-flop, we need to complement it every time. So what we do, we connect the count enable to the J and K inputs of this flip-flop. So this is always 1 when the count enable is 1. So this will always keeps complementing. For the next flip-flop, we connect A0 dot the count enable through this AND gate. So this is ANDing A0 here with the count enable, and this will be 1 whenever A0 is 1. So whenever A0 is 1, J1 and K1 will be 1s, which will make A1 complement. Same thing exactly, the J2 and K2 will be equal to A0 and A1 through this AND gate. Again, ANDed with the count enable, and for the next one, J and K will be A0 dot A1 dot A2, and so forth. Finally, we can, when we reach 1, 1, 1, 1. On all the flip-flops, there will be 1 which will go to the next stage if we need to connect stages with each other. We can also make an up-down counter using the same method that we have just described. However, in this example, we use T flip-flops. Again, we have A0, A1, A2, and A3, and the common clock again is connected to all the clock inputs of the flip-flops. And here we make this counter to count either up, which means it will go from 0, 0, 0, 0 to 1, 1, 1, 1, or make it count down, which means it will go from 1, 1, 1, 1 to 0, 0, 0, 0. Let us see how this counter works. Suppose the count up is 1 and the count down is 0. Actually, when the count up is 1, this here will be 0. And therefore, we don't care what is the count down. This will be 0 here. And when this up is 1, it means this is 1 here. And this is 1. And this 0 makes this 0 here. And this is 0. And this is 0. So the OR gates, you find one input will be 0. This input here. And this input here. And this input here. And the other input will be connected to the other signals, which is the up signal here that is 1 initially, which means this is 1. And then when this is 1 and this is 1 here, this will be equal to A0, which means this will be A0, and this will be here A0, and this is A1, this is A1 and A0, etc. So simply, what we mean by this, when up is 1, T will be equal to 1 with the first flip-flop, and this will always complement. This will complement when A0 is 1 and up is 1. So this will be A0. And this will complement when A0 is 1 and A1 is 1, and so forth. So the counter will count up exactly as we have just described for the JK flip-flop. On the other hand, now, if we would like to use it as a down counter, we make down equal to 1, and up will be 0 here. And when this is 0, this will be 1, and this will be 1 here. So this will be 1, and this is 0 here. So this is 0, and this is 0, and this is 0, and this is 0. Therefore, all these AND gates will have output of 0, and the inputs to the OR gates will be obtained from the other signals, which is ANDing the down signal, as we can see here, with A0 prime. This is A0 prime, and A1 prime here, and so forth. So when the counter starts with 0, 0, 0, 0, as an example, this here will be 1, 1, 1, and 1. And the inputs to the AND gates, this will be here 1, and this will be 1, and this will be 1, this will be 1, and this will be 1, and this will be 1, which means T of all the flip-flops will be 1s, and therefore the counter will change from 0, 0, 0, 0 to 1, 1, 1, 1, which is as expected. So the countdown goes from 0, 0, 0, 0 to 1, 1, 1, 1, and after 1, 1, 1, 1, it will go to 1, 1, 1, 0, which means in the next count pulse, this only will change from 1 to 0, and so forth. It will go to 1, 1, 0, 1, 1, 1, 0, 0, and so on. We continue. So this is the up-down counter using T flip-flops. We can design a synchronous binary coded decimal counter. So this is a BCD counter, and it is synchronous, so we use the clock. We can design it actually the same way we studied earlier, design of sequential circuits. So in this design, we use T flip-flops just to change, and The way we do it is as follows. First, we start with the state table. So we write down the present state, which is from 0000 to 1001. That's the binary coded decimal. And the next state, when this is in state 0, it will go to state 1. When it is in state 1, it goes to state 2 in binary, and so forth, state 3. And when we are in state 8, we go to 9, and 9 goes to 0. We usually also provide an output here. We call it Y, which is 1 when we reach the final count, so that we can cascade, we can put more than one stage when we need. If we call the flip-flops Q8, Q4, Q2, Q1 respectively, where Q8 is the most significant and the Q1 is the least significant, we can easily derive the values of the flip-flop inputs, which is TQ8, TQ4, TQ2, and TQ1. And we simply find that TQ1 will always be 1, because if it is 0, it goes to 1, and if it is 1, it goes to 0. Similarly, we derive the value of TQ2, which is, again, the first time it will go from 0 to 0, so TQ2 is 0. Next time, 0 to 1, so TQ2 is 1, and so forth. We derive it this way. And we derive also TQ4 and TQ8 exactly in the same way, which is looking at the present state here and the next state here. And if the present state remains same as next state, T is 0. And if it is changed, T is equal to 1. So from this, actually, we can easily now continue the design of this counter. We have written here this again, just so that we can see it. We find that TQ8 is 1 in 2 different combinations, which is 7 and 9 here. So if we call this TQ8, this kernel map, it will be 7 here, and it will be 9 here, and 10, 11, 12, 13, 14, and 15 will be don't cares. Same thing, we go here to TQ4, it will be 1 at the 3 and the 7. So that is the 3 here, we put 1, and that's the 7, we put 1. Again, we put don't cares in the same 6 positions, and then we move on to TQ2, which is 1 at 1, 3, 5, 7. So we write here 1, 3, 5, and 7, and we have don't cares in the remaining 6 positions, and TQ1 will be 1 in all 10 different positions. So these are ones, and these are don't cares. So this is the simplest. TQ naught is equal to 1, and we can derive, TQ1 here, and we can derive TQ2 here, and TQ4, and TQ8, and finally, we can say this is Q8, this is Q4, Q2, and Q1, and this is the clock here, all connected to common clock. And finally, the T of each flip-flop will be implemented as we can derive from these different kernel maps. So this is one as an example here, and here we have this loop and this loop, and here we have this loop, and we are done with the design.